Hello there, kids. It's your best buddy, Mr. Munger, here to bring a lot more science excitement. And I've delivered to you this evening the Friday problem of the day. I figured we would get some more practice on reaction order. I'm trying to get things together here with our crystal violet and sodium hydroxide so we can eventually get that lab done that really puts these reaction rate order ideas to work and do it in a way that I can pull it off here in the garage. So let's get moving along onto this problem here. So we got a generic ABCD reaction. So we're looking at our two reactants here, A and B, in molar concentrations. And we've done 5 experiments and gotten 5 different rates. Well, they're not all different, but what we're going to do is to figure out what would be a generalized rate law based on the data here is that we take our baseline trial, which is trial 1, and then we start successively comparing the changes that happen from there to garner if these two reactants either of these two reactants have no effect on the changing rate. That would be a 0 order. If an increase in a reactant causes the same increase in the rate, that'd be first order. Or if an increase in a particular rate winds up increasing that rate squared, which of course would be a second rate order. And from there we can write a generalized rate law for this particular equation. So we would have rate equals our constant times whatever order A is going to be. We haven't figured it out yet. Whatever order B is going to be. We haven't figured that one out. So let's take a look at some of the ideas that we discussed today. So what we do is we first take a look at experiment 1 and then see how, say, experiment 2 compares to it. And as you can see, we have a change here in A. Then down the road, we may see how 2 and 3 compare, or 2 and 4 compare. And so those trials may validate the data that you got at the first comparison or not. And then, of course, you'd be looking for changes with the other reactant, B. So let's stop the camera for a minute and see if you can figure out whether A and then B is a first, a second order, or a 0 order. Give you a couple minutes. All right, so let's take a look. So when we compare trials 1 and 2, you can see that we doubled the concentration of A, and notice that that also has a corresponding doubling of the rate. So that is a first order pattern right there. We see that validated between experiments 2 and 3, where we double the concentration again and we have a doubling of the rate again. So they're going up at the same level. That's first order. However, when we look at B over here and over between trials 4 and 5, we doubled the concentration of B, but notice there was no change to the reaction rate. So that would be 0 order. Also, if you want to note, between trials in 3 and 4, we halved out the amount of A, and correspondingly, the rate went down by half, and more evidence that A is a first order reaction. In that case, we're working in reverse. And notice that even a doubling of the B did not offset in any way the decrease in the rate due to the corresponding decrease in A. So we would write that this order is rate equals K times A to the first power times B to the 0 power. And in reality, what happens is we normally cancel out 0 orders, and we just write a very simplified rate equals K times A. There we go. So armed with that, we can figure out what K is. We can take any one of these 5 trials and apply our newly derived rate rate law that is, and solve for K algebraically. So let's take trial 2. We could take any of them. So if we have our rate is 0.04 equals K times 0.8, we just simply solve for K, and K is 0.5. And if it's truly a constant, we could do this in every single trial and we would get K as a 0.5. So with this particular arrangement, you should be able to solve either for overall rate laws, for the individual rate orders for each reactant, and also you can, once we've determined the rate law, we can determine the actual identity of K.